Today we'll continue talking about small cancellation theory for Burnside groups for groups of Burnside type. This is the name of my talk, the title of my talk. Okay, so still we'll be talking about small cancellation theory. So the next part will be about Burnside group themselves. But we finished with at some point where I have to define was defining small cancellation theory of a small cancellation group. So, but okay, today I would like to start with a general idea, with this right-hand general idea, then which actually this general idea can be seen from what I was talking before. So that's a general idea of small cancellation, some general idea. So what I want, sorry, is to present some version of small cancellation theory in some simple combinatorial language. So okay, some people define small cancellation theory in terms of action of some of a group or some on some space which is hyperbolic which is hyperbolic or close to hyperbolic. But okay, I don't want to do this, and I would like to present it in a simple combinatorial terms. And so actually I formulated three parts of my small cancellation condition, and okay, so and I denoted them C naught, C1, and S naught, S1, and S2. So I look at my notes. Okay, so this, and I formulated in a general form. So we have some condition. So what we have? We have a group, say G naught, a group. And we have another groups which we want to have to be small cancellation over G naught. So G1 is G naught over some set of relators. See, okay, let's denote it by R1. Okay, or the normal closure of some set of relators R1. I'm using this one here because I can assume that we have also set of defining relations for G naught. So for G1 it will be R1, and we have three conditions. So S naught is so we in some sense we have some set of reduced words, of reduced representatives of elements of the group G naught. So we have some set of reduced words, and we have also some set of cyclically reduced words. So I assume that each R in the new set of relators is cyclically. So I write it in quotes because it's not defined. So it's some general things and some general idea. It's cyclically reduced with respect to G naught. So some cyclically reduced representative. So we have another condition. All relators are sufficiently large with respect to this group. Each R is again in quotes sufficiently large okay with respect to actually I wrote it in a more precise form. Sorry. So R, if R belongs to R1, then the size of R1 belongs is greater or equal some parameter omega, which is a parameter which we don't know what is it. And S2 is this main part of the small cancellation condition. So I formulated, if you remember, I formulated, provide three formulations, three different views on this condition. One is combinatorial view, another one is diagram view, and yet another one is Cayley graph view. But okay, let me just write this combinatorial form of this condition. So because okay, yeah, I use this geometric two geometric forms just to explain what does it mean, and now I just write it in a combinatorial form. So if if R1, so we have two. Okay, actually I have to introduce a symmetrized set of relators. So R1. I denoted it by R1 by head is the closure of R1 under cyclic shifts and taken the inverse word and taken inverses. Okay, now actually I called this words from this set relators. The set of relators. Relators. Okay, so we have two relators. And they so in the classical small cancellation condition we have this the common subrod of them, but in our version we have closed subroots, and close means okay they have some relations of this of the following form. So if Ri is say Si Ti, so this is a quality of plurals. And if S1 say is equal to U S2V in this group in G0, and again in UV some are in some sense are small. So this means like informally means that have a geometric closeness of these two subroots of R1 and R2, and okay, and if at least one of them is sufficiently large compared with the whole relator, so this means that if S say 1 is big enough, say lambda, so lambda is the main parameter of the small cancellation R1. So okay, is this all? Looks like okay. Then, so the consequence of this is that just we have this relation R1 is we have conjugate relators. U R2 U to the minus 1. So and geometrically this means if we have some close pieces of boundaries of two cells which are labeled by these relators in the Van Kempen diagram over this presentation of G1, then we have a cancelable pair, and we can remove this pair and replace it with this diagram over G0, so we have this reduction. So okay, this is main small cancellation condition. We have several parameters of this. Okay, this is general idea, and we consider now the case of a small cancellation over a small cancellation group. Small cancellation over small cancellation. Two-step small cancellation group. And try to make this general idea precise for this case. So what do we have here? So we have G naught is a small cancellation group. Say we have a representation with the set of relators R naught. So it's a small cancellation, and okay, I already defined the small cancellation condition. So we assume that it satisfies, say C prime over lambda, where lambda is some small number, say lambda less or equal to 1 over 6. Okay, and okay, we have the same thing. We have G1. So what does it mean to be cyclically reduced in this case? Already explained it, and for set of reduced representatives in with respect to this group, I just take the set of then reduced words. So that I already gave the definition the last time. I just say it in words, and this is then reduced means that a word is, first of all, it's really reduced, and this and it doesn't contain any piece, any subword of the relator which is more than a half of this relator. So this means then reduced, and okay, just for then reduced, I just take, so for cyclically reduced, I just take cyclically, for cyclically reduced, I just take cyclically then reduced. So okay, let me just replace here this general condition with the particular case for when we have G naught as a small cancellation group here. So okay. I just checked if I switched on recording, so that I did. Okay, just replace here is cyclically then reduced with respect to G naught. Okay, this condition is still remains, but okay, that's what I noted. What I said about this condition. So actually, we have to use here another definition of the length. So it's this is the thing I will be just talking about right now. So okay, and this condition, what does it mean to be small? Again, what does it mean to be small? And actually, okay, I already explained this. So what this definition of to be small, how it comes? It comes actually from consideration of so-called bygone relations and triangle relations. So, for example, if you consider bygone relations, so there, what does it mean? If you consider relations of this form, so suppose we have a just relation of the form x equals to y in this group in G naught, where x and y are then reduced. Well, just let me say, because actually I will use this this condition to be then reduced several times. Let me just write it as G naught reduced. Okay. Then reduced in G naught is the same as G naught reduced. Okay, and this cyclically G naught reduced. And G naught reduced. Okay, and we have when we consider the corresponding Van Kampen diagram, which describes this relation. This means that we have a Van Kampen diagram which is labeled. We have a disk Van Kampen diagram which with label of the boundary loop x, say y to the -1. And this is the consequence of the small cancellation condition is that this is a single layered diagram. So it looks like probably like this. This is a picture, so it's so these are cells of the Van Kampen diagram, and we have, say, x here, and we have y here. So these 2 points corresponds to the points of the Van Kampen diagram where x starts and x ends, and of course y starts and y ends here. So the path which is labeled by x and y. So to be precise. Okay, this is how this Van Kampen diagram looks. And okay, but if we consider, so this is this consequence of the small cancellation condition, and if we consider a diagram of a Van Kampen diagram over this presentation of the group G1. So let me draw some picture of this. So for example, let's assume that this consists of 3 cells which are labeled by relators from this set. So let me draw like this. This is but okay, this is just 3 cells. But if you consider if you consider a Van Kampen diagram over this presentation, so we have 2 sorts of cells. One sort is are cells which are labeled by relations of the group G1, and another one are cells which are labeled by relators of this group G0. And because we have this condition of the new relators of this from R1 are large in some sense, so we have large cells and small cells. So let me, and actually picture looks like this. So there are some small cells here. Something like here. Okay, and if we assume that our label of our boundary is then reduced with respect to this group, so we have picture like, and we have picture like this. So these are small cells and big cells. Okay. If you want to, so this is actually so how do we consider this? So how this small cancellation condition for this type of diagrams? So instead of common pieces of boundary of cells, which are labeled, which are labeled by these relators, we have some close segments of this boundary. So, for example, you consider these 2 cells. So let me use this red color. So we have this subdiagram which corresponds to closeness of these 2 segments of the boundary. So this, and this, if you consider label of this diagram, so this we have this one. So we have, okay. So we have one piece of boundary, say S1, another piece of boundary of another cell S2, and we have this path labeled by S1 is equal to, say, U and V. And UV are labeled by words which are subwords of relators. U and V. So the small, in this case, for small we just take small we just take subwords of relators of this group G naught. So let me introduce the set H, which is a just subwords of the set of relators. So we have actually two sets of relators. So we have subwords of set R naught hat. Okay, this is again we have this set of relators R naught, and we have the closure of the set under cyclic shift and taken inverses. So we have this set of subwords. I denoted by H. And actually, okay, let me call them bridge words. Bridge words. So, in this case, for this condition, I just take this one. U and V belong to H. Okay, and what else? So okay, the idea is that we take this words from this. We take these subwords of bridge words. Also, okay, actually I have two names for this. Let me and also I call them pieces. So we have two. These subwords have play two roles in this relators. These are like bridges. And actually, now we see that actually they have another role. So the point is that this word is considered as small, and if we want to define this, for example, this length, then this any subword of this any word from H, any subword from relator from this set should be considered as small, and okay, it's, at the same time they can be very large words. For example, if this set R naught is infinite, that it can be this piece can be arbitrarily large in the sense of usual lengths of words. But at the same time we have to consider them as a small. So. This justifies the following definition of the length. So consider any word W, and I call a fragmentation of this. The definition a fragmentation of W is a representation, so it's just a partition of fragmentation of W. So I have to do this. Is a partition of this this word into subwords. So is W is representation, say x naught, x1, x2, say x, say k. So it's just the equality, graphical equality of words, where xi is either a letter, or letter means, okay, we have this set of generators, so letter means that we have a letter from a generator or its inverse, or xi is a piece. Piece in the sense that the subword of the set is a subword of some relator of this group of this group G naught. Okay, and we introduce a weight of this fragmentation. Weight of W is so. The point is that we consider a piece. We assign to a piece some constant length, and just the simplest thing is just to consider this to assign to a piece a length 1. So this means that we can, if you count the length of this rod, so we have just we count the number of pieces. So this number of pieces in this fragmentation. Oh, sorry, fragmentation F. This is a weight, not just a word, but this is the weight of a fragmentation. So it's a number of pieces in F and plus number of letters. But letters are considered as small entities. So this way, we count them with some coefficient, say zeta, number of letters. With zeta is some small parameter. So this is a weight, and we consider now the lengths. So some new lengths W, and we call it the length of W with respect to G naught. So I use a subscript. I use the subscript G naught here, and this is just a minimal possible weight of a fragmentation of this word. Is minimal weight of F, where F is a fragmentation of W. Okay, and actually what I have to use here, I use the new definition of the length here. I have to use here the length with respect to this set of relators G naught. So I put here everywhere subscript G naught, which means that I have this. I use this new length. So if you look at this condition now, we'll see that actually, if you consider any relator of this group G1, then if you try to extract pieces from these relators, so to consider any fragmentation of this, so this means that it's sufficiently large with respect to if you count, okay, if with respect to all relators of the group G naughts here. So this means that if the number of if you consider a Van Kempen diagram like this, then the number of possible small cells of this diagram which surrounded some cell which corresponds to this relator should be very big if you just surround it by all small cells like this. So this is the relevant measure of how we measure lengths of rods with respect to the group G naught. Okay, and actually this is the same thing. This is the same thing here. We have to use this G naught, this new length here. G naught and G naught here. Okay, and now what we get here is a formal definition of some condition which depends on parameters, on 3 parameters here: big omega, zeta, and lambda. So we have a small cancellation condition. Remember this small cancellation condition, which depends on 3 parameters. say lambda here, omega and zeta. Okay, if you, other questions actually, if you want to, if you have questions, just ask me.
Я прослушала, извините, зета большой или маленький параметр?
Но zeta это маленький параметр, это какой-то, то есть буквы, letters are considered as small or small compared to the pieces. Okay, let me give an example. So the theory, the small cancellation theory, example, this small cancellation, okay, let me should abbreviate it like this. Theory works for lambda is less or equal 1 over 24, omega, so it's actually we don't consider just the bound on omega, but we consider this lambda times omega is greater of or equal than, I think, 20, and zeta is equals to 1 over 20. So this is an example, and this for this set of values, I know I know that the theory works. Okay, actually I have to explain what does it mean to theory to work. But why do I know here? Because actually this set of parameters is for this set of parameters, this theory works for much more general case of iterated small cancellation condition. Actually, I never tried to check which conditions on this parameter we need to for this small cancellation, for this simple case, for this two-step small cancellation theory to work. So I don't know. I never checked it. But if you okay, this it's a kind of an exercise, and then when everybody can check this. But okay, it's of course it's not easy because we have to develop this small cancellation theory even in this case. But anyway, so that but okay, this case this values work, and this values work in much more general general situation. So actually we for this two-step small cancellation theory we need probably some weaker values. For I think for example I think that it should work, for example, for lambda less or equal than 1 over 10, and zeta say equal to 1 over 10 or something like this. Okay, so just an example which surely works. And what does it mean for the theory to work? So we have, as I explained, for one of there are several consequences of small cancellation which are like common for all small cancellation for all small cancellation groups. For example, there should be one of this main consequences of this small cancellation theory should be a version of of the then property. So how this version, how this generalization of then properties, how does it look in this case? Okay, if you look at this picture, so if you look again, so let's try to understand it in some intuitively. So, for example, we have these three cells, and because we have this small cancellation condition, this means that these parts, this common, like not common, but these close parts of boundaries are small compared to the boundary of this each of this cell. So this is not bigger than lambda, this is not bigger than lambda, and this is not bigger than lambda times the whole boundary here. And this means that the remaining parts, the exterior parts of this boundaries are big enough compared. But okay, we don't have this like a classical dead property, but we have this again. We have closeness here. So if you look at this picture, and now if I formulate formulate this generalization of the small of the then property, then actually it's clear why should I formulate this then property in this way. Just I'm going to do. Okay, let's let me erase this one. So the consequence. Generalized then property. So the exact formulation is like this: if say x is equal to what is the trivial represents the trivial element of the group G1, and x so x should be reduced. You can see the G naught reduced, and what else? Okay, non-empty. Then, so it contains like a more large part of relator with of the large part of this relator. Then x is say x1 s x2. So this is a subword s, and this also we have a relator, some relator R is equal to say I don't know PQ, which is belongs to let's have not enough. Okay, just R equal to PQ belongs to R1, so it's a relator of this group, where S and P are close. Oh, no, not X. S and P. S and P are close. G not close. Okay. Okay. This I have to define this, but okay. This is actually what I use here. G not close. And P is large enough compared to R. And P. Actually, I actually formulate the precise statement here, and precise statement says that the length with respect to G naught is greater or equal than 1 minus 9 lambda times the length of the whole relator R, again with respect to G naught. So okay, that's if you check and okay, this is the statement that I know to be true, because it actually can be formulated in a much more general situation for iterated small cancellation condition, and this is just a special case of this. And if you look at this, if lambda for this case lambda is less or equal than 1 over 24. And 9 times lambda is okay. What is this? Is 3 over 8. And we have more greater or equal than 5 over 8 times the length of R. This is more than a half. This is again this generalization of that property. If we have a word which represents the trivial element of this group, and this is if this is reduced in the base group G naught, then actually it contains more than a half of a relator, 5 over 8th part of the relator, but with respect to this length, with respect to the length of which is defined with respect to which is defined like this. So this is the generalization of that property. Okay. Конечно, да.
Вот там слева есть равенство. Во второй строчке S2 мы заключаем, что R1 равно U2 U минус 1. Да?
Да.
Вот заключение мы делаем в группе свободных.
Да. In G naught, да. This is I have to correct it.
И тот же вопрос вот про то, что мы сейчас обсуждали. всегда его уже теперь делаем в группе G0, да? То есть мы пишем.
Здесь графическое равенство. Давайте я буду использовать специальный. Let me use this special notation for graphical equality, which is traditional, like equality with the small circle in the center. So this. Look, here we have graphical equality. Here we have graphical equality. But this is equality in G0. Okay, because okay, actually, let me repeat what does it mean to be G0 close. Let me use it. Okay, with this definition. X and Y are G0 close if X equal to U, this Y, V, where U and V belong to in G0, where U and V belong to H. So this is the picture precisely like this. We have here we have equality in G0. So okay, is it clear? Okay, so here we have this equality in G0, but here we have graphical equality. You see that we have. Okay, let me now use another color. So this is this equality. This is the piece of boundary of the cell. This is piece of this is a piece. This corresponds to S. This corresponds to P. This big P. And this is this small U and V. Here we have U. Okay, this is S is equal to, yeah, here we have U, which is a piece, and here we have V, which is actually empty. So this shows how this S and P appear. Okay, now so this is one of the consequences. This is a real small cancellation theory which works. Now we would like to come to iterated small cancellation theory. So we iterate this. Okay, this is what we do. This is what we want to do for Burnside groups. And let me. Okay, let me use this space here. Iterated small cancellation theory. So how much time do I have? So what we have here, what the situation? We have a sequence of groups. So we have G naught. Now G naught just a free group. Nothing. Okay, and G I is equal to G I minus 1 over a subset of relators R I. Right? Actually, let me, and I is traditionally called the rank, but let me, so this in our school. Rank is usually denoted by alpha. This comes from Novikov-Adyan theory. So let me use this. At least we have. I will always use the letter alpha and beta and so on for rank. So we have sequence, and Okay, actually we have a group, and we have group G infinity, which is defined by all relators of all ranks here. So this is our group which we want to somehow to consider as a small cancellation group, but we have a sequence of this level groups. Okay, and we want to formulate some small cancellation condition for this case. So okay. What we have here, so we need, and we do in a way that we did in the case of small cancellation over two-step small cancellation. So we need this length x with respect to the group alpha, but let me just denote it by just by the subscript, which is the value of the rank here. The length of some words of a word with respect to the group G alpha, and we have also some notion of reduced word. But let's come back for a moment for this two-layer small cancellation. So we have this dead property, and from this dead property we can just see what can be taken for the new notion of for an analog of the then reduced word. Just if we can consider some notion of a reduced word with respect to G1. So a word with respect is reduced with respect to G1 if let's look at this if cannot have this this subword S, which is a clause in G0 to a subword P, to a piece P of some relator of R1, and which satisfies this property. So actually, okay, but we have to look something more general. So we have a parameter here. So we just introduce a parameter because this is just like a special. This is just a statement for some special value of parameter, but we introduce a general parameter. Okay, so we have. So let me introduce a notation like red, the set of reduced words with respect to the group G alpha, the set of reduced words. Reduced words in rank alpha. So instead, with respect to the group G alpha, I will always say that it is something in rank, in the corresponding rank, in rank alpha. Okay, and what do we need more? What do we need more? So we have this set. We would like to define the set of bridge words. But let's look at this some diagram, some Van Kampen diagram of the presentation, say, of the group G alpha. So we need to define what do we need to define? Is a small cancellation or a condition of a group G alpha over the group G alpha minus 1. And if you consider some Van Kampen diagram over the group G alpha, if we assume that it is a small, if we assume that it's a small cancellation group, then okay, we have several layers, we have several types of cells. So we have cells of rank alpha, which are cells which are labeled by relators of this set. We have cells of rank alpha minus 1, which are labeled. So these are the cells which are labeled by relators of rank alpha minus 1, and so on. So we have also relators of rank 1. So we have several types of relators of cells in our Van Kampen diagram, and actually this we assume, we intuitively assume that every time we increase the rank, the cells become bigger and bigger. So we have this. If you consider, for example, this cells as rank is cells of rank alpha. Then we have cells of rank alpha minus 1. But we have cells of rank alpha minus 2, which are much smaller than the cells of rank alpha minus 1. Okay, which are very small here. And okay, so you, of course I cannot draw them as cells, but if you look at the picture, there are very small cells which can be between cells of rank alpha, cells of rank alpha minus 1, and so on. Okay, this is the picture like this. So, and if you try to look at this general situation like this, so actually this piece of the closed piece of this subdiagram, which is which corresponds to two closed pieces of boundary of two cells of rank alpha. So actually we can look that way. This U and V are labeled are paths which are labeled not just pieces of rank alpha minus 1, but so we have this piece of rank alpha minus 1, but between piece of rank alpha minus 1 and this is S1 and S2, we can have also pieces of rank alpha minus 2 and so on. So actually this explains that we need to define a new set of bridge words which are called H alpha, bridge words of rank alpha, is by definition is what? So it consists of the set of U, S, V, where U and V are bridge words of the previous rank, and S is a piece of rank alpha, is a piece of rank alpha. So what do I need to define here? Of course, I have to define H naught. It's just a set consisting of a single word, empty word. So again, we have this group G naught, and this is just a free group for closeness. So this H alpha, these are bridge words these are words which we use in the definition of close words in the group G alpha. If you have the group G naught, then it's just a free group, and closeness means not just coincidence of just equality in this group. So G naught consists of empty word, and G alpha for each next value of rank alpha we have this definition. U, S, V, where S is a piece of rank alpha. But a piece of rank alpha, you already used this definition. A piece of rank alpha is just any subrod of a relator of rank alpha. Okay. Any subrod, okay. So this is the definition of bridge words, and now we have the notion of close words of rank alpha. Let me use some space here. So I don't want to erase this, but let me use this space, which is less important. So two words X and Y are close in rank alpha if X equals to U, Y, V, where U and V belongs to this set of bridge words H alpha. Okay. So we have closeness, and now we have this one. Okay, that's but we can now define the set of reduced words of rank alpha. using this analogy. But actually, we for the set for this, you see, if we want to define the set of reduced words of rank alpha, so we need to use the length of word which is defined in the previous rank. So actually, so you see, to define this this set for rank alpha, we have to use this definition for rank alpha minus 1. And actually, for this definition of in rank alpha, we have to use the definition, as we see later, we have to use the definition of reduced words for rank alpha minus 1. So actually, we have to define these two things, we have to use joint recursion here. So assume this set R, the set of reduced words in rank alpha minus 1, and this definition are defined. Actually, we have to use this we have to define this for the value of rank 0, right? But if for 0 it's clear, so red note is just the set of really reduced words in the set of generators, of course. And the length is just this the usual length of a word. Nothing. So okay, we define this, and okay, let's buy. So, definition: X belongs to reduced. X is reduced in rank alpha if and only if, first of all, it should be reduced in the previous rank, and if X. Okay, let's not write. Let's not write. If X equals graphically equals, like this, X1 as X2 and some relator R alpha, R alpha hat here is also graphically equals to PQ, and S and P are close. S and P are close in rank alpha minus 1. Then, and also if then P cannot be large. And P, the length of P in rank alpha minus 1 is less or equal where some parameter rho of the length of all of the whole relator R. You see, rho is another parameter here. Rho is a parameter. For example, actually, we can take for this parameter 1 minus 9 lambda. You see, if here I erase the statement, the generalized dead property for this value of this parameter. I'm sure if we have a strict or not strict equality here. Okay, I don't care. Let's write it. Not strict equality. It doesn't matter. Okay, is a parameter that, actually we can take this just for this parameter which have take this value. Lambda is a parameter which we use here. This is the main parameter of the small cancellation theory. We can take this one. Okay. So we have, you see, we define the set of reduced words of rank alpha, and we assume that we use here the lengths of words with respect to the previous level group here. Okay. Now we have this one. We define this one, and we have to define this one. Let's define it here. So the set, but we need one more definition, and this is okay. This is actually a very it's an important notion of the small cancellation theory, and I call it this notion I call a fragment. A fragment of rank alpha is a word, say, is a word x such that x is close in rank alpha minus 1 to a piece of rank alpha. And what? And the important thing is just x should be reduced in the previous rank. So this is an important notion, and actually here we have we can reformulate the definition of reduced word. So a reduced word in rank alpha is a word which is reduced in rank alpha minus 1, such that it doesn't contain a subword which is a fragment of rank alpha, but which satisfies this, which is large compared to the whole relator in this sense. And now we have this definition of this this length. So we have, in a similar way, we define a fragmentation of rank alpha of some word. So if we have a word here, place. Let's try. Let me try to use this space. A fragmentation. So fragmentation f of rank alpha of a word w is a representation, a graphical equality x1 xk, where xi is a piece of rank, say, beta beta I less or equal than alpha. So, oh sorry, not a piece, of a fragment. So we have just this partition. Oh no, it's not true. It's a subword of a fragment. This is a little, is a subword of a fragment. It's a subword of a fragment of rank beta I less or equal to. So what we do here, we just partition a word into subwords, such that each subword is some fragment of rank which are less or equal than our fixed value alpha here. And actually, you see, it's a generalization for the case of two-step small cancellation. But actually, in the two-step small cancellation, we also have letters here, right? We have pieces and letters. Now we have fragments. Okay, let actually look what we have. Okay, we have to use letters here, and this means that I have to introduce a fragment of rank 0. It's just a formal thing. Fragment. Let me erase here. Unfortunately, this set of definition cannot be written in this piece of the board. So I have to erase something. So a fragment of rank 0 is just a letter. So we have here we have also fragments, letters which we consider fragments of rank 0, and we consider fragments of all ranks which are less or equal than alpha. Let's actually look what is a fragment of rank 1. A fragment of rank. This is by definition rank 1. So, okay, let's look at this definition. A fragment of rank 1 is a word X which is reduced in the previous rank, which is reduced in rank 0. It means that this means nothing more than just a freely reduced word, and which is a close in rank 0. And close in rank 0, we already know that it's just a equality in this group G naught to a piece of rank 1. And every we will be assumed that every piece of every relator of rank 1 is cyclically reduced in the previous rank. It should be cyclically reduced. So okay, this implies that every piece of rank rank 1 is a freely reduced word. So we have two freely reduced words which are close in rank 0. This means that which are equal in this group G naught, and this means that they just coincide. So a fragment of rank 1 is a piece of rank 1. So it's a subword of a relator. And if you consider this, the value of rank equal to 1, then the fragmentation in this definition is nothing more than just a fragmentation as we defined for the case of two-step small cancellations. We have letters and pieces, and fragmentation is just partition of words into letters and pieces, and that's it. So, but a fragment, we consider a value of fragment equal to, then we have here we have can have also fragments of rank 2, and this is not the same as a fragment as a piece of rank 2, because a fragment okay, let's look at this definition. A fragment of rank 2 is a word X which is reduced in rank 1, so which is actually which is then reduced with this parameter, and which is close in rank 1, and closeness in rank 1 is not a coincidence of words, is an equality of the sorts. Where is it here? Close in rank 1 means that we have this small words here. So it's not just a coincidence, graphical coincidence of words. We have this with this non-trivial words U and V, because we have this set H. I erased the definition, but H1 consists of all pieces of rank 1. So this is so for the next step we have more general thing here. We have a fragment of rank 2, and again, and you see here we have a subwords. And why do I have subwords here? Because if I use subwords here, then actually this length, as I define here, let me actually define the length in rank alpha. Let me define this thing, and actually it's defined precisely in a similar way as we define the length for the case two-step small cancellation. So the length, okay, that's of W with respect to the group G alpha, so denoted like this, is the minimal. Okay, I have to define the weight. Sorry, the weight of a fragmentation. F is what is the following thing. So number of pieces of rank alpha. The weight depends on the rank. The weight with respect to the weight in rank alpha of rank. Let me abbreviate it. N alpha plus. Now we have the same parameter zeta here. Zeta. No, sorry. N alpha plus zeta n alpha minus 1 plus zeta square n alpha minus 2 and so on plus zeta to the alpha times n naught, where n beta is the number of fragments of rank beta here. So we count fragments of rank alpha. Okay, let me write it here. N sub beta is beta is not very like to beta. Okay, is number of fragments of rank beta. This means, okay, we count fragments of rank alpha with weight 1. We count fragments of rank alpha minus 1 with weight zeta. We count, sorry, we have alpha minus 2 here. We count fragments of rank n alpha minus 2 with weight zeta square. We count letters with weight zeta to the alpha, and zeta to the alpha, and you remember I write for zeta, actually I take this 1 over 20. This is a small number here. So okay, and now we can define this one in a similar way. The length of rod in rank alpha is the minimal possible weight of a fragmentation of rank alpha. The minimal possible weight of rank alpha of a fragmentation of rank alpha of this rod. So this is defined, and okay, we define these two things. So and I explain why I take subwords here, because if I take subwords, then we have some nice properties of this length. For example, if we have a subword, if say x is a subword of y, then x, the length of rank alpha of this word is less or equal than the length of y in the length of y. Why? Because we have subwords here. If we have a fragmentation of a word y, then we also have a fragmentation of any subword of this word, because we have subwords here. So it's close, and they take the fragmentation like we can come from a fragmentation word to a fragmentation of any subword here, and we have this. And okay, we have the weight with the weight of this fragmentation for x will be less or equal of the weight for the fragmentation for y. So this implies this, because we have the subwords here. This implies, for example, this nice property of this length. So okay, what we did, we defined this one, and we have to define. Finally, we have to define the small cancellation condition. So we replace this small cancellation condition for the two-step small cancellation group with the corresponding with the analogs for iterated small cancellation. So we have is cyclically reduced in rank alpha minus 1. So why what does it mean cyclically? What is cyclically reduced if each cyclic shift of the word is reduced? So this is okay. This is like a natural thing. If we have this one, okay, R alpha, then the size of this word alpha minus 1 is greater or equal than omega, some parameter. And okay, then we replace this condition with a similar one. Consider our alpha here. So alpha here in this condition is, okay, they just, no. We replace this completely with this one. In G alpha minus 1. This is alpha minus 1. So we consider this, we compare two subworlds of relators in the group of the previous rank. So they have alpha minus 1 here and alpha minus 1 here, and this alpha minus 1 here. And this actually, this is complete formal definition of our iterated small cancellation condition. Okay, are other questions on this? So it consists of three parts: S0, S1, and S2. S0 says that each relator of rank alpha is cyclically reduced in the previous rank. This condition says that this R is sufficiently large, where the length of R is taken with respect to this defined length, to this length in rank alpha minus 1, with respect to the group G alpha minus 1. And this is this main small cancellation condition we replace just we formulate it in this general case. So what we get here, we have a small cancellation condition which depends on several parameters here. Let me list all these parameters here. So first of all, we have parameters of the reduction. Okay, depending. Actually, for rho, okay, depending on rho. What else? Omega. What else? Zeta here. And lambda. So the main statement, okay, it's not just a statement, but actually it's just a meta statement. It says that this theory works for the values of parameters which are already have written. So rho equal to 1 minus 9 lambda. Lambda less or equal than 1 over 24. Zeta is equal to 1 over 20, and we have this for omega we have this inequality. Lambda omega is greater or equal than I think 20. This one. This is not okay. That's not. It's not very. It's not far from usual small cancellation parameters we see. For usual small cancellation group, we take lambda 1 over 6, but we have lambda over 24. So it's not just it's not that one over 1,000 or like this. So it's like a reasonable set of parameters, and so this is the definition. And actually, I think it's a good point to stop today. And the next time I will say more about the small cancellation condition, and probably the next time I will start talking about Burnside groups. Why the Burnside groups are satisfy this small cancellation condition. Okay, then why this theory can be applied to Burnside groups.